Hi everyone, and welcome to Feasibility and Architecture of a Dual Board Embedded System, Yocto and Zephyr Integration, which sounds like a fancy title, but don't worry, this presentation focuses less on jargon and more on the practical journey from the initial concept through hardware and software development, culminating in a fully operational system. Let me start with a quick introduction to our company. We work at Amarula Solution, a software consulting firm. Among our services, we work on embedded software. We prioritize and focus as much as we can on open source. A few words about me. I'm Andrea Ricchi. I am an embedded developer from Carpi, Italy. My expertise lies in user space application written in C or C++, as well as UI framework, UI application using Qt and the Flutter framework. I also have hands-on experience on Yocto and Buildroot, and I have some contribution across Yocto, Buildroot, and some C++, some C code like Conman, and yeah.
Hello everyone, I am Dario Binacchi. At Amarula, I mainly work on creating and adapting the BSP for the board we support. I am an open source contributor for projects like Buildroot, Yocto, Linux and U-Boot, and I come from northern Italy. This presentation will describe our experience from the first idea to the final implementation, and we'll share the challenges we met along the way. We'll begin with the Yocto build system and the Flutter UI framework for the main board. Then we will cover the Zephyr operating system and the LVGL for the sensor board. And finally, we will show a short demo, a short video for a quick overview of the demo. Before diving into what I just aligned, let me spend a few words about the origin of this talk. It was November 2024, and at Amarula we had to decide what to present at the Embedded World 2025. Our target was to showcase the technologies we are familiar with, the principles guiding our engineering decisions, like using software packages as close as possible to the mainline version, and also put in evidence that we are ST partners. So starting from these ideas, we decided to build a thermostat application where a main board communicates, collects and displays ambient data from a remote sensor connected to a sensor board, communicating with the main board over the CAN bus. For the main board, we choose the NGCAM EDIM starter kit based on the STM32 MP257 module, which allows us to use Yocto, Linux for the operating system, and the Flutter UI framework to develop the graphical interface. While for the sensor board, we selected the STM32 F429 Disco board, but despite its more limited resources, it was a good fit for running Zephyr as the operating system and LVGL as the library to develop the graphic interface. The MP2 module includes several peripherals, like CAN interfaces, multimedia processing, and a 3D graphic processor, making it a good fit for our application and ready to use as the main board. Things were quite different for the sensor board. The discovery board does include built-in sensor for ambient data, and what's more, the microcontroller, despite the microcontroller features two CAN peripheral, the board design doesn't provide access to CAN bus for external communication. So we needed to add a sensor for the pressure, another sensor for the temperature and humidity, and finally a transceiver for enable the CAN bus communication. Then our other colleague, Alberto Bianchi, created an extension for the discovery board, he connected the sensor to the I2C bus. He enabled the CAN peripheral by removing some components from the discovery board to avoid hardware conflicts. And then he added the CAN transceiver to enable the communication. As you can see in this part, As you can see in this part of the schematic of the disco board, the USB OTG pins are shared with the CAN pins. So we had to cut some lines to enable the CAN peripheral. In the image on the left, there is the top side of the sensor board showing the discovery board, the sensor, and the CAN bus connector. While on the right, there is the bottom side of the board. On the left, the connection between the microcontroller and the CAN transceiver, and on the right, the connection from the sensor to the I2C bus.
Okay, so when building embedded system on NCU, we need something that was flexible, scalable, and above all, reproducible. So how do you build your own Linux distribution perfectly tailored to your hardware? We selected the Yocto project. It doesn't just serve a ready-made meal. It gives you all the ingredients, the recipe, and the tools to create what you need every time. With a rich ecosystem of open source maintained package and layers, Yocto strikes the right balance between maintainability and customization. It's package-based, giving you full control over the image and the toolchain, and it enables reproducible builds, which is critical when working on BSP generation for real-world products. For our projects, we started with the fundamental layers, the Open Embedded Core and Meta Open Embedded, which provides the essential building block for our image, everything from standard utilities to package management. Since we are targeting an ST module, we included the ST-relevant layers, which provide the kernel, board support, and base operating system. On top of that, since the board is designed by NGCam, we also added the Meta NGCam ST, which includes the device tree and the board-specific configuration for our hardware. Then, to support our Flutter-based UI, we integrated the Flutter framework with the Meta Flutter and its dependencies, the Meta Clang. And finally, we have our own custom layer where we maintain the application recipe and any project-specific implementation. The main challenge that we faced when working on this Yocto project was a version incompatibility between the Meta Flutter and the Meta NGCam ST. The Meta Flutter was on the ScarpCut version, and of course, we wanted to keep everything as up-to-date as possible, also to be able to bump the Flutter framework as much as we can. So, with a few tweaks of my colleague Michael, we successfully updated the Meta NGCam ST, porting to ScarpCut, allowing our project to run on the latest Yocto version, LTOS version. To ensure a consistent and smooth build process, we customized our local .conf file. Of course, we selected the machine and distro based on our module and hardware. To speed up task execution, we added the number threads and parallel makes settings. Since we're targeting an ST MP2 module, we accepted the EULA, which required to enable access to specific ST layers and binaries. For localization, we enable UTF-8 locales and specified language support. We selected the Debian package format. That is the way Yocto install packages inside the image, and we choose Debian since we are pretty comfortable with it on embedded. To support reproducible build, we also configured the deterministic root file system, which ensure that every build is identical no matter of when they are run. The configuration also enables extensible SDK generation, which simplifies the application development and set up the PR server to avoid version rollback when packaging the image. The recipe, not the image. Finally, we extended our image install with the Flutter UI component, the Flutter engine, and the Flutter Wayland client. More on that later. We also added our custom application and our custom CAN library, also more on that later, and the command manager to handle Wi-Fi connectivity. Of course, we also added the Flutter framework to the Yocto toolchain. And with this file, this configuration, everything was ready to be built without any more configuration or any more tweaks, and was ready out of the box. As you've seen so far, managing Yocto can get complex. There's layers, there's configuration, there's dependencies, and it adds up quickly. Cache is a tool that streamlines Yocto development by letting it manage you everything from layers, repositories, configuration, and much more through a single YAML file that is version controlled and well structured. So instead of manually handling each layer and tweaking local setup file, Cache lets you define a structured, version controlled, everything in a structured and version controlled format. With a single command, Cache build, you can go from a clean machine to a fully built image Linux without needing any tweaks or changes. It's especially useful in collaborative environments or in continuous integration pipelines where reproducibility and fast setup are essential. You can think of Cache as a lightweight project manager of Yocto. It keeps your workflow clean, reliable, and repeatable. And by combining the power of Yocto with the simplicity of Cache, we ended up with a single YAML files that looks like this. So we have our YAML file. Of course, we define our machine distro and target the same way that we defined in the config file before. And also, we defined all the layers and the version that we wanted to target, and also the local.conf configuration. So everything is version controlled, which is really important when working together, structured, and ready to be built with a single command. This setup is really clean, and it's a simple file, but it's doing a lot of heavy lifting behind the scene. That said, using Cache is extremely easy. With 2 commands, you can clone and build. And another key feature is the Docker integration, which lets you run all the Cache commands in a cleanly isolated environment, keeping your host untouched. Also, the container feature is really useful, of course, on CI, so you don't have to mess with host tool and such. Once our robust Linux system was in place, the next critical step was to choose a modern UI framework that could match its performance and provide a modern user experience. And that's where Flutter comes in. For those who don't know, Flutter is a UI framework developed by Google and written in the Dart language. Is extremely popular in mobile app world. And you might be thinking, Flutter, that's for mobile app. I've heard a lot of people saying that it's not supported on embedded. Also, I didn't hear a lot of Flutter during this conference. And so we are here today to bust that myth. It's not supported, but it's already shipping in real products from major brands like Toyota and other stuff. The Flutter experience starts with a revolutionary developer experience. You can imagine designing, building, and perfecting your application on desktop because Flutter is fully cross-platform, and getting instant feedback with features such as hot reload, so there's no need for flashing, for waiting, and we develop our entire UI this way. Also, another key point regarding the multi-platform is that you can get user experience and application that feels the same no matter the platform. So if you need embedded in mobile or embedded in web, that's a great point. And this process dramatically increased the productivity and allowed for rapid iteration. And then being modern is extremely easy to learn and has modern language features such as the null support, the null safety, and async and await support. This means that your application is robust and safe. It's practically impossible to create a segmentation fault in a Dart application. And the async await support means that it's almost impossible to have your UI application hang or freeze. The magic of Flutter is that it's natively compiled. This means that there's no compromises on performance. What you build on the desktop runs with incredible speed on the board. And one more thing, you don't have to build it all from scratch. Flutter is fully open source with a massive and thriving community. And you can think of it as a treasure chest of pre-built components that you can get on the pubdev site. For our project, we pulled packages for page indicators, color schemes, and state management. And on the slide, you can see some more examples. The Get package is a fully featured Flutter framework that provides navigation support, translation, and a lot of useful features. There's widget charts, fonts, animation, and Flute Keyboard, that is my personally maintained package. It's a virtual keyboard for embedded projects. So without reinventing the wheel, we had a great UI components or more complex framework. Of course, when working on embedded, we need to talk to the hardware. For our CAN communication, we needed to touch the low-level system. And with Flutter standard component, this wasn't so easy to achieve. But this is where Flutter elegance truly shine. With Dart foreign function interface, or FFI, we created a seamless bridge between our native C++ library to our Flutter UI application. This gave us the best of both worlds, a beautiful and modern app in Flutter, and the powerful and performant hardware control in C++. Cleanly separated, but perfectly integrated. And on the slide, you can see on the top the public API of the C++ library. In this example is the get temperature getter. And on the bottom, you can see the Dart code that dynamically loads the library and then calls the getter. So we have a modern framework with a huge ecosystem, but now comes the question that everyone is thinking: how hard is to actually integrate into my Yocto build? We all know that integrating new and complex framework can be hard, a battle of recipes and dependencies, but with Flutter it's not a battle, it's a click. With the meta Flutter layer, you don't have to become an expert on how the framework engines build system work. You simply add the layer to your project and you are ready to go. It's designed by the community for seamless integration and is widely adopted and supported by major brands. One of the main contributors to Meta Flutter is the Toyota. So yeah, great stuff. So with the Meta Flutter also, of course, provide the Flutter SDK, which can be easily added to your Yocto toolchain, and it handles all the cross-compilation. Then there is the Flutter engine. You can imagine the Flutter engine as that piece of code that is between the base operating system and your application and handle all the Flutter's functionality. Then there's the Flutter embedder, and the Flutter embedded is that piece of code that open your application bundle and integrated the function functionality to visualize the application. There's a lot of choice. If you need an X11 less embedder for Raspberry Pi. There's Flutter Pi. If you're building more complex application or infotainment system, there's the EV on screen from Toyota or the Wayland Flutter client from Sony. For our project, which used the Flutter Wayland client, the integration was flawless, and everything was pretty easy, and it turns the complexity of the Flutter framework in just 2 lines. Finally, for your application, you can simply take the Flutter recipe that are already present in the framework, in the MetaFlutter, and customize based on your need. The key line is the inherit Flutter hub that handle all the cross-compilation and the bundle generation when working in Yocto.
So let's now continue with the sensor board, moving to the operating system. It was clear from the beginning that Linux would not be the right choice. Even if the board is supported in the mainline Linux and has a build root configuration, we need an operating system with a smaller footprint to keep enough resources for the graphical interface. Zephyr, on the other hand, already supports the board, and also with our first test on the touchscreen and the display with the example application confirmed that the drivers were implemented and working properly. In addition, Zephyr also has support for the kconfig and the device tree, allowing us to customize the board for the application needs. So at the end, Zephyr was for sure the obvious choice. At this point, our first question was, how do we properly design a Zephyr-based application? Zephyr uses CMake as its build system, but is application-centric. This means that the application controls how it and the kernel Zephyr get configured and built. In the application directory, we have 3 files, 3 key files. The CMake list file tells the system where to find the application sources and link the application to the base system. Then the add.overlay file contains the changes to the device tree in order to adapt the Zephyr board to the application needs. In our case, it turns our discovery board in the sensor board. And finally, the prj.conf contains application-specific configuration options. It is a kconfig fragment file that gets merged with the Zephyr-based configuration during the build. In Zephyr, application can be categorized in 3 types, depending on where the application is located. We have a repository application in case the source code is located inside the main repository. We have workspace application if the code is outside the main repo, but inside the workspace. And finally, we have the free standing application in case the source code is totally outside of the Zephyr workspace. We choose the Zephyr, the workspace application because we didn't want to change the source code inside the main repo. This way, we can always use the mainline version of Zephyr without to worry about conflicts from our code application. Then, following the example application on GitHub, that is a reference for how to structure a Zephyr-based application, we set up our workspace. We clone Zephyr, the required module, for example, the LVGL library, and the source code of our application. Now I'll go over the file used to configure and build the application. Starting from the CMake list file, the find package command loads the Zephyr build system, which creates a CMake target of name app. Then we can add the source files of the application to this target through the target sources command. And finally, we can build the application running the west build command. About the DTS overlay, we can say that we added the sensor to the I2C bus at very specific address. Then, as we did for the hardware, by removing the components from the discovery board to avoid the hardware conflict, we had to disable the USB OTG node because it shares the pin with the CAN peripheral, and then we enable the CAN device. As often happens in the Linux device tree, no description was required for the CAN transceiver. About the prj.conf, we enable all the kconfig options related to the subsystem required from the application. So the I2C bus, the sensor, the CAN bus communication, LID, and graphical library. You don't see any specific setting related to the driver we used, like, for example, the big scan controller, the different types of the sensor, and also the driver we used, because Zephyr, the build system of Zephyr enable automatically it. We will go into more detail later on this topic in the section about the graphic library. Regarding the application layer, Zephyr and its modules provide a clear and simple API and a lot of example application for the different subsystems, from the CAN to the display and to the sensor. These example applications were very useful for us for testing the hardware, and their code was a good starting point for our application development. About the application development was also an opportunity for us to contribute to the Zephyr project. Due to a regression in Zephyr, the CAN controller clock, one of the CAN controller clock wasn't enabled, so the peripheral didn't work properly. We found and fixed the issue, and then following the Amarula approach, we upstreamed the patch to share it with the community. While we were waiting for the patch to be accepted, we applied locally the fix in the DTS overlay. And once the patch was accepted, we removed the fix and we updated the manifest to the first version of Zephyr, including our fix. We can also mention that we upstreamed other patches for improving and fixing the board documentation. While these patches were not as critical as the one that affected the device functionality, they still provide unuseful support for anyone who is working on this board. And now let's take a look at the graphic library. LVGL is a free and open source library, providing everything you need to create an embedded graphical interface with a lot of easy to use graphical elements and with a low memory footprint. It comes with a wide range of widgets, from label to text to buttons, and supports device input like mouse, touchscreen, and keyboards. It is written in C. It works with any driver and with any hardware and display. And what's really matter for us, Zephyr can package with LVGL. In Zephyr, the LVGL source code is split among two locations. It is downloaded automatically by the West update command in the workspace module, which makes it to keep easy to keep it updated and separated from the application. Under the Zephyr modules folder, you'll find the integration layer, which contains a specific Zephyr configuration and glue code. These layers handles tasks like kconfig option settings, initializing the library at the system startup with the LVGL init function, and select the display through the device tree with the DT chosen macro. About the display configuration, all we needed to do was to enable only the kconfig options related to the display subsystem. We are using the ELI9341 driver from Elitech, and thanks to its kconfig dependency generated by Zephyr B system, it is enough to use the right compatible in the device tree to have the kconfig related to the specific driver automatically enabled. Indeed, we can confirm that in the .config file, you can find this option enabled. On the TTS side, we didn't do any changes because the hardware was already set up by the device tree of the discovery board. What is great here is that the use of the Zephyr display property and the settings under the LVG_pointer node are used by the LVGL init to turn on the touchscreen and the display. So when the application starts, everything is already up and running. This means also that if you change the hardware of the display, you don't have to change the code of the application because all the configuration is covered by the device tree. And now, before jumping into the interface development, there is one more thing we have to do. So we have to enable the graphic library. We have to enable only the widget really used by our application and tweak a few kconfig options to fine-tune the memory setup. About the interface development, we can say that the core idea in the LVGL is that everything is an object. So the code is all about creating and configuring this object. About the implementation, without going too deep, we started from the basic data flow description that you can find in the LVGL documentation, and we added only the 0.5 and 0.6. So we updated the widget based on the data coming from the remote sensors. If you consider that the first three steps are totally handled by the integration layer of Zephyr, the developer only needs so create the graphical interface, update the widget based on the application logic, and keep calling the LV timer handler function to process the internal to run the process the internal processes of the library and refresh the screen. Zephyr provides also a memory footprint analysis. This table compares 5 use cases, starting from a minimal example, that is the Hello World application, and moving on to more complex application, some including the UI and other not. We can see that in all the cases, including the UI, the SDRAM usage for the frame buffer is always the same. And more in general, that the memory footprint stays small, even in the most demanding cases, showing that the library is a good choice for the mid-platform range, like the one we used for our application. In addition to the static analysis, Zephyr provides also a runtime memory profile by enabling the shell kconfig options. Zephyr provides some commands, LVGL stats memory, that show how the heap is organized and its usage, including the free memory, the used memory, and the amount of memory that it is used to handle the heap. In addition, with another kconfig options, the monkey kconfig, Zephyr provides some monkey commands which are able to inject to the input devices a random event. All these commands were really useful for us for fine-tuning the memory setup, test the UI automatically, and identifying runtime issues like memory leaks or unexpected behavior. Then I will show a quick overview of our demo. We start from the... Huh? Oh. We start from the sensor board. We are exciting the temperature sensor. When we interact with the graphical interface, we move to the hardware of the main board, and then we interact with the graphical interface of the main board based on the Flutter UI. Me and Andrea want to thank people that helped us to develop the application, like Michael Trimarchi and Eduardo Gonzalez. And as a quick note, you can find all the code we developed under the hands-on section in the resources section. So you can try, if you want, to download and see what we have done. That's all from our side. Thank you for your attention, and we are happy to answer any question or curiosity.
Zephyr, and did you try this? Because then you could use the same, maybe the same framework.
Yeah. So the question is, first of all, how would you compare Flutter to Qt, and if Qt is supported on Zephyr, right? Yeah. So. From the code point of view, probably Qt is a bigger framework because it also have more C++ classes, also to handle more low-level stuff. But in my experience, the transition from Qt to Flutter was really easy. And from the coding point of view, it's pretty easy if you're already comfortable with QML. And the result, honestly, I prefer the Flutter result from the UI point of view. Regarding Zephyr, I don't know if Qt is supported on Zephyr. Usually, yeah, there's a commercial version for Zephyr, so you need to pay. Yeah. Yeah.
You didn't mention anything about the IPC between these two, between the microcontroller and the Flutter running process. So how was it? Just CAN. So how was it configured?
You mean the CAN communication from the
So you would need an IPC process on Zephyr as well as on.
About the, sorry?
You would need an IPC process. I mean, what kind of?
No, we communicated through over the CAN bus, the main board with the sensor board. Are you meaning the communication between the main and the sensor board?
Yeah,
Yes, we sent.
Yeah, we just send the CAN packages that contains the data information of the sensor. So the application, the LVGL application also handle the data reading and sending the package through CAN, and the Flutter application using the C++ library handle the incoming packages and yeah, displaying the data.
It was just CAN messages.
Yes.
Yes, raw CAN
raw
without a
messages.
specific protocol, no CAN open, nothing, raw commands about the sensors, the value of the sensors. So this was the reason why we don't go into the detail about the CAN communication.
Yeah.
What would be the concrete steps to port this onto a mobile phone or a web server or something?
The Flutter application.
Yeah, the solution basically.
The Flutter application, you can simply recompile on the target and it runs. It's really, really easy. I mean, the application runs on my desktop and runs on the embedded, and if you target a mobile device, Android or iPhone, or if you target the web interface, it's all handled by Flutter. So the application runs without any problem.
Yes, but in Flutter is all bare metal, a native book to get the CAN.
Oh, regarding for the CAN, we also, if you configure the CAN library, because the CAN library has a configuration file that you can tweak. So if you have a USB to CAN adapter on the laptop, you can work with it. Most of the application was developed that way. So we first developed the sensor board with the CAN communication. We hooked the sensor board to the PC using a CAN to USB interface, and the data is read without any issue. Yeah. So I think there are no more questions. Yeah, go ahead, Michael.
Yes. No, I'm curious about the question that he made about Qt 5 and Flutter, the experience that you have, and I want to know if, because I'm not a graphics expert, I don't write C++ and Qt, I want to know if, in your experience, is faster to prototypes and modelize an applications, UI application, because we are focused now on UI because we compare to graphics toolkit in Qt, or is faster to test and deploy and modelize in Flutter?
Okay, so the question is if it's easier to prototype and create a Flutter application or a Qt application. Probably a Flutter application. It's a modern framework. It comes with really handy features. As I said, null safety, async support. On Qt, if you're not an experienced programmer or you start messing up with the QML code, putting logic inside the QML, the application freezes, and it's quite bad. In Flutter, it's impossible to do that. Everything is handled via events and async. So yeah, it's probably better, in my experience, to work with Flutter than Qt from this point of view. Okay, thank you again.